Hi everyone, I'm Shankali Pradhan and today I'll be talking about identifying optimum liquid to solid ratio range for microcrystalline cellulose-based formulations in twin screw wet granulation. We'll first talk about continuous twin screw wet granulation and a regime map approach. We'll then look at some experiments on MCC containing formulations using twin screw to identify a range of optimum liquid to solid ratio. We'll look at the granule growth behavior for this experiments, and then we'll use this data to define regime map boundaries of undergranulation, overgranulation, and paste formation. Wet granulation in general can handle challenging to compress drug substances as well as high drug load formulations. But twin screw is unique in the sense that it offers intense mixing or shear, so uses less granulation fluid compared to some other methods of wet granulation. The residence time is very short, just of the order of a few seconds, and it is a regime separator operation, meaning a material goes in and out with no rewetting of granules or unpredictable recirculation in the high shear section. The screws themselves come in the form of screw elements of various geometries, so you can mix and match them to change the screw configuration and tune your granule properties accordingly. The granule size distribution and solid fraction are the two key granule properties that we look out for. So we want to prevent bimodal distribution, or we want to avoid excess fines to avoid any flow issues or segregation downstream. We also want to control over the granule solid fraction because it controls tablet compaction, disintegration, and dissolution. The liquid to solid ratio and the screw configuration are the major parameters that affect these granule properties, and screw speed also to some extent. We're going to look at the liquid to solid ratio because it has a strong influence on the size and solid fraction of granules, as well as operating outside a good range can result in several operating challenges such as pasting or jamming, or result in too many fines that cannot be fixed downstream and cause clogging or flow issues downstream. So for high shear wet granulation, a regime map approach has been very successful in defining optimum liquid to solid ratio ranges. So this is how the regime map for a high shear wet granulation looks like. We have pore saturation on the x-axis and Stokes deformation number on the y-axis, which is the ratio of the kinetic energy imparted to the granules divided by the dynamic yield stress, which is the resistance to deformation. And based on the growth rates of the granules, we have different boundaries of growth regimes, and we can see all sorts of growth regimes from dry free-flowing powder all the way until slurry or paste. Now, the physics of high shear is very different from twin screw, so we will need to construct a new regime map for twin screw wet granulation. And an excellent foundation was laid by Denge et al. When they made this regime map. They have liquid to solid ratio times binder viscosity on the x-axis and a parameter beta on the y-axis. Beta is the deformation value, which is the ratio of the granulator torque to the volume of the material in the barrel, which is the input energy given by the granulator on the material, divided by the dry granule strength. Now, this twin screw regime map is a great beginning, and we can improve upon it in many ways. We can define these regime boundaries based on some quantitative relevant criteria. We also need to replace the dry granule strength with a wet granule strength in order to be more representative of wet granule physics inside the granulator. And if we are able to replace the granulator torque, which is typically an output parameter from the granulator, by something that is an input parameter or something that can be measured on a small scale, then we can make this regime map predictive in nature. So here's what we need to do. We need to develop quantitative criteria for defining the boundaries. We need to study granulation over a wide range of liquid added, and we need to develop a small scale method based on either formulation properties or input process parameters so that we can predict these regimes a priori. In order to do so, we did experiments on the twin screw using these model formulations with acetaminophen as model API, Avicel as the model excipient, and a binder in the powder phase. The granulating liquid was just plain deionized water, and our screw configuration is the standard kneading element screw configuration with two kneading zones in 60-degree forward angle separated by a conveying section. This is how our granulation looks like at different liquid to solid ratios. We go from everything all the way from dry, free-flowing powder, all the way until clumps and finally paste. This is how the granule size distribution of these formulation looks like. On top, we have high MCC containing formulations, and on the bottom, we have low MCC containing formulations. And we can see that for the same liquid to solid ratio, the low MCC formulations gives much larger granule sizes compared to the high MCC formulations. We can also see a difference in the growth behavior of these granules. And if you look closely, the range of operable liquid to solid ratio becomes smaller and smaller as the amount of MCC in the formulation decreases. This means that if you have more MCC in your formulation, then you will need more granulating liquid. And that makes sense because MCC itself absorbs so much liquid that it leaves less liquid available for actual wet granulation. And that is shown in these formulations as well. The growth behavior becomes clearer in this curve. We have plotted the mean granule size as a function of liquid to solid ratio. And the growth of the granule is almost exponential for the lowest MCC formulation. And as you increase the microcrystalline cellulose content in the formulation, the curve becomes flatter and flatter and eventually becomes a plateau, where the hypothesis is that the granule growth is governed more by the granulator geometry rather than the formulation itself. So we'll be using this data to formulate our regime map. Our regime map will identify different granulation behaviors such as underwetted, good, and overwetted, as well as paste formation. We'll use some quantitative criteria to define these boundaries. We'll have pore saturation on the x-axis and a Stokes deformation number on the y-axis, similar to the high-shear wet granulation regime map. The dynamic yield stress is going to be the small scale parameter that we measure on the lab scale, and it will be normalized by some relevant input process variables so as to make this regime map more predictive. So the first step is defining the undergranulated region of the regime map, and we are going to use the percentage fines to define the undergranulation, because the percentage fines only increases during downstream operations such as drying or milling, and can only be set low at the twin screw stage. We know that large amount of fines can cause clogging issues during drying or flow and segregation issues downstream. So we've defined fines to be anything smaller than 90 microns, and we've set the maximum limit to 5%. When you plot the percentage fines as a function of pore saturation for all these formulations, you can see that it lies on a universal curve. These data points seem out of trend, but it's an artifact of the measuring method. We've used sieve analysis, and it gets difficult to sieve extremely undergranulated conditions for high API content, with API being a micronized API in it. So these definitely look out of trend, but these are undergranulated. When we define a maximum limit of 5%, we can see that anything under the pore saturation of 0.4 is essentially undergranulated. And there we have it, our undergranulated regime of the regime map. We've defined overgranulation as granules that are not quite paste yet, but they're still big enough to be causing issues during process such as extended drying time or not being able to fluidize at all. We've set a maximum limit on the granule size based on minimum fluidization consideration. So we have our Ergun equation over here. And as the wet granule density changes as a function of increasing liquid content in the granules, we can define a maximum size of the granules that can be fluidized when the dryer of your choice is operating at 80% of the capacity, for example. And this is how the maximum allowable granule size looks like as a function of pore saturation. When we overlay that with the D50, we can see that for low MCC formulations, we have certain regions that are at a risk of overgranulation. So now we've defined our overgranulated region of the regime map as well. In order to define paste formation or paste points, we look at the mechanical properties of wet compact. For low saturation or near saturation, the material is an elastic plastic material with a stress strain curve that looks like this. We have a clear elastic region where we can define an elastic modulus, and we have a peak stress, which is the dynamic yield stress, and that is what we're going to be using for constructing our regime map. But when the material becomes a paste, it deforms completely plastically. You cannot define an elastic region for a material like this, and neither can you define a dynamic yield stress. So what we did was we prepared compacts of wet material at different liquid to solid ratios and deformed them or crushed them using a compaction simulator. And this is how the deformation looks like. It goes from all the way from brittle at very low liquid to solid ratios to paste at very high liquid to solid ratios. And the corresponding stress strain curves looks like this. So here we can predict that the material will form paste at a liquid to solid ratio of 0.7 for this material. So we did this for all the 4 formulations, and this is the liquid to solid ratio predicted for complete paste behavior using the small scale method that I just described before. And when we compare that to the liquid to solid ratio at which paste was actually observed on the twin screw during operation, it matches pretty well. We can also convert this liquid to solid ratio into a pore saturation for all the formulations. And you can see that for these formulations, the pore saturation at paste point is approximately 1. So now we have all the regions of our regime map. We have the undergranulated region at pore saturation of 0.4 or lower, and paste formation at pore saturation of 1 and higher. And our overgranulation is defined using minimum fluidization criteria. So if we overlay our D50 of the granules on these regions, you can see that the D50 is very low for undergranulation. You don't have granules for paste formation. And then we can define, identify regions which are at a risk of overgranulation using this regime. So this is how our final regime map would look like. We have Stokes deformation number on the y-axis, which is the ratio of the input process parameters to the dynamic yield stress, which is measured on a small scale, and pore saturation on the x-axis. And the great thing is that the Stokes deformation number also follows the same trend as D50. So you have small Stokes deformation number for undergranulation, and then you cannot define a yield stress for pore saturation of 1 and above. So this is a great beginning to an improved regime map that we could use, and it's a feasible path forward for us. Here are a few guidelines on how you can construct your own regime map and use it for wet granulation. You would first need to define what are fines based on the particle size of your blend, as well as define an allowable limit of fines for post-processing. You'll need to do some scouting experiments to determine at what pore saturation is the cutoff for the allowable limit of fines. Paste points can be identified using the small scale method I described before. And for these formulations, it was 1, but it will change based on liquid surface tension, viscosity, or the blend components. An overgranulation regime can be identified by performing dryer calculations for a dryer of your choice. And you can use your scouting experiments to identify actual regions of overgranulation. As we add more and more formulations to this regime map, it will become more predictive and will have limits on the Stokes deformation number as well. So there we have it. We've defined regime map boundaries based on relevant criteria for undergranulation, pore saturation of 0.4 or lower, overgranulation using minimum fluidization criteria, and pasting using a pore saturation of over 1. Of course, this regime map is a good beginning, but it needs a lot more work. We need to incorporate different screw configurations and fill levels in the granulator. We also need to incorporate different water-based binders with surface tension and viscosity, as well as different formulations that are even non-MCC based formulations. With that, I'm ending my talk, but I'm open to questions. Please contact me. My contact details are listed here. I'm Shankali Pradhan. I work for Vertex Pharmaceuticals. I work extensively on oral dosage, formulation development, and I also help in particle engineering for the drug substance with a viewpoint of developing better formulations. I look forward to any questions. Thank you.